Hello everyone. I'm going to work through an example that's a little bit complicated. It's going to be showing you how to calculate capacitor waveforms for voltage, current, power, and energy. And this is very similar to a very typical problem that we assign on the final exam. So now here we're given a capacitor of value 500 microfarads, okay? We're given some current flowing through it, and that's given by this waveform here, this current waveform. So it's showing the current following this funny pattern, right? Like so. And then what we want to do is find the capacitor's voltage. So what's the voltage in response to the current flowing into the capacitor, okay? So we want to find the voltage, and we also want to find the power and the energy as well. And these are all going to be in terms of waveforms, okay? So now we're going to see how we're going to solve that. Okay, so now we're assuming that there's zero initial charge on the capacitor, and what that means is that its initial voltage is zero, okay? So if there's no charge on a capacitor, okay, there's no electric field, and the voltage across that capacitor is zero. Okay, so how do we go about solving this? Well, we're given the current, okay? We're given the current, and we want to find the voltage, and we have the expression that we found in the last lecture, that the voltage is equal to 1 over the capacitance times the integral of the current plus the initial voltage, okay? So we're going to use this expression to find the voltage. Okay, so now, how are we going to go about it? We're going to examine each time interval separately, okay? So we're going to do what's called a piecewise analysis, and then, so what does that look like? So we're going to look at the time interval 0 to 2 seconds, right? And then that waveform, the current waveform, is 20 milliamps. Then we're going to look at the time interval 0 to 3 seconds, and that current is 0 milliamps. And then we're going to look at the time interval 3 to 5 seconds, and that current is minus 20 milliamps, okay? We're going to do this piecewise analysis. Okay, so now let's do the first time interval, okay? So that in that first time interval, the current was 20 milliamps. And I've put the equation up here, and you'll notice that we've done a change of variable because we're going to want to calculate the function for voltage, okay? We're starting at time 0, and we're ending up at some arbitrary time in the future, so t is a variable, okay? So then, let's see what our next step is going to be. Well, we were given that the initial voltage is 0, so that term is going to get zeroed. Okay, so then what is I of t? How do we represent that current as in its function, as a mathematical function? And it just represents 20 milliamps, okay? So that's just 20 times 10 to the minus 3, okay? So then, if we implement our equation, then we have, we have RC coming down here. This is our current, right? Which represents this. And then we calculate the integral. So then, in summary, we have the capacitance, right? We have the current, the integral of the current, and then since the current is a constant, that can come outside, and that's what we have here, and that's going to resolve to 40, okay? And then when we take the integral, we're going to solve it, and we're going to get the v of t being equal to 40t, okay? So that's just going to be a straight line, okay? And then we can calculate at when it's at 2 seconds, what's the value going to be? And the value is going to be 80 volts. And we can just denote that over here. Okay? So that's our first piece of our piecewise analysis, and we have the voltage for the first time interval. So we're going to leave that graph on the bottom, and we're going to calculate the next time interval. Okay? So the second time interval is looking at between 2 seconds and 3 seconds. And what we notice, the equation that we're going to use to calculate, so now as the lower limit we have 2 seconds, and we're going to take the initial voltage at 2 seconds. That makes sense. And then we're going to go up to t. So we're going to repeat our analysis. So I of t is, in this case, it's going to be 0, right? Because we have 0 milliamps in that interval. And then, so when we calculate v of t using the equation, we see that the integral term goes to 0, v of t goes to 80, and we know it's 80 because that's what we found in our previous piece that we analyzed. We found that point, right? And that's how we got this 80. Okay, so then our v of t is just a constant. It's 80 volts, okay? So then that's why we draw a straight line here, and the function is v of t is 80, okay? So then, let's do our last time interval. So our last time interval is from 3 to 5 seconds, and our limits go from 3 to t, and we're taking the initial voltage to be at 3 seconds. Okay, so then, I of t in this case, well, it's going to be minus 20 milliamps, because that's what this is right here. It's minus 20 milliamps. Okay, and then when we plunk in our equation, we have the minus 20 milliamps here, so don't mess up the minus sign. We have the V3, and then when we work that out, we get a little bit more complicated integral, and then we finally solve it to get v of t is equal to minus 40t plus 200. Okay? So then that's a straight line, and that appears here. Okay? So that's the last segment of our piecewise analysis. And we can confirm that when we're at 3 seconds, this function gives us 80, which is our starting point here, which should match the previous piecewise analysis. And when we hit 5 seconds, then we should get 0 volts, which we do right down here. Okay? That's a cross check. Okay. So then, what do we know? Okay, we're going to actually do the power now. Okay, so we're going to calculate the power in the capacitor. Okay, I've drawn out all the waveforms, and this is what we were given. Okay, so that was in the original problem statement, so that's what we were given. And then when we did our analysis, we calculated this in the previous step when we did our piecewise analysis. Okay, so the voltage waveforms are the calculated values, and in this case now we're going to calculate P of t. So we're going to do this this plot. Okay, so let's see how we're going to do that. How do we calculate the power in a capacitor? Well, we know that power is simply voltage times current. Okay, so then, do we have the voltage and the current? Well, we do. We have the current in this waveform here, and we have the voltage in this waveform here. So there's different ways that we can solve this, and one of the ways is just graphically. So these are two graphs, and you multiply the graphs together. Okay, and you can do this visually, or we have the mathematical functions for each piece, and we can multiply those together. So we can multiply first two together, the current and the voltage, then we can multiply the second two together, and then the third two together, okay? And that's what we're going to do. Okay, so let us do the first time interval. So we're doing the first time interval here, okay? We're calculating the power, and then our equation is power is equal to voltage times current. So then when we're doing voltage, right, when we're doing voltage, we're taking this voltage here, 40t, okay, putting in our equation. And then when we're doing the current, we're taking this current up here, minus 20 milliamps, and that's this part right here, okay? We're just multiplying them together, and we get the power being equal to 0.8 T, okay? So what does that look like? Well, let's calculate what the power is going to be at 0. It's going to be 0, and at 2, it's going to be 1.6 watts, okay? And then we can plot that line here, okay? So right down here is the line P of t is equal to 0.8 T. And we've put the value of 1.6 watts up here. So the line rises up to 1.6 watts. Okay, so then let's do the next interval. We're doing the interval 0 to 3 seconds, okay? So then we know the equation, it's voltage times current. The voltage in that interval is 80, so that's this 80 here, and then the current is 0, and that's this current up here, okay? Works out to 0. So then, if the power is 0, we draw the power like so. It's 0, and it starts from up here, so it must go straight down, okay, at 2. So we have to interpret that and go straight down. Okay, that one was pretty easy. And then, let's do the final interval. So now we're doing the interval 3 to 5 seconds, okay? So then, we take the voltage waveform, so that's this one, okay, and that's this one here, okay? And then we take the current, minus 20 milliamps, minus 20 milliamps here, okay? So that's where we get those from. Multiply them together, and we get 0.8 T minus 4, okay? So that's the current waveform. So what does that look like? Well, let's calculate the 2 points, okay? So at P is equal to 3 seconds, we get a minus 1.6 watts. That's kind of interesting, right? So it looks like at 3 seconds, it's jumping down here. And then at P is equal to, well, P of 5, or when, what's the power at 5 seconds, then we get 0 watts, okay? So it goes to here. So what does that function look like? Well, it looks like this. Just a straight line, so it drops down at 3 seconds and rises up in a straight line to 5 seconds, okay? And you can notice, you know, minus 4 is its y-intercept, okay? So it makes sense the way the line looks, right? Because it's kind of shooting down here if we continued it. Okay. So now we know that. Let's think about what's happening here. So this part of the power graph is positive, okay? So this is positive, okay? And what's the capacitor doing? The capacitor is storing energy. So how can we see that? Okay, well, current's flowing into the capacitor, and what's happening is the magnitude of the voltage is increasing. It's increasing. So it's getting charged up, okay? The voltage is increasing because more and more charge is going and charging up that capacitor. Okay, so that's our first clue. The voltage is increasing. Second clue is that the power is positive, Okay, so think about a resistor. A resistor dissipates energy and its power is positive, right? I squared R, it's always positive, right? So now, what's happening with the resistor, it'll be taking energy from the circuit, okay, and dissipating it as heat, but it's taking energy from the circuit. So now, the power is positive for this capacitor, and what's happening is the capacitor is also taking energy from the circuit, except what it's doing is not dissipating it as heat as a resistor does. What it's doing with that energy is that it's storing it in its electric field. Okay, so a positive power for a capacitor means that it's storing energy. Now, let's look at the converse. Negative energy, negative power, I beg your pardon. Negative power, so that's going down, negative power in a capacitor means that it's delivering energy. So it's supplying energy to the circuit, okay? Now, when we looked at voltage sources, I know they can go, they could be supplying or delivering, but let's say the typical, let's say it's like a battery and it's charging up, or it's providing energy into a circuit, it's negative power, okay? So similarly, the capacitor's power is negative when it's supplying energy back into the circuit. The stored energy is being released back into the circuit. We can also see that it's losing energy by the magnitude of the voltage going down, okay? The magnitude is decreasing, okay? So it's losing energy. Okay, so that's that part. So now we've calculated the power waveform, we've calculated the voltage waveform. Now let us calculate the energy in the capacitor. So how are we going to do that? What's the relationship that we know? Or what are the relationships that we know? So we actually know two. One is the one that we did most recently. Its energy is 1/2 CV squared. Okay, and the other equation that we have is over here, and that is energy is the integral of the power over the time interval. Okay, that's what that's saying. And then plus whatever initial energy, let's say that capacitor had. Okay, so we could use either of these two equations. I wonder which one will be easier to use. Okay, for this one, we need to know the voltage, and for this one, we need to know the power and the initial energy. Okay, so which one's easier? So let's analyze it both ways. So we're going to do the first interval. Okay, so the first interval is here, 0 to 2 seconds. Okay, and what does this equation look like? So energy is going to be 1/2, so that's the 1/2, right? And then this is the capacitance, so that's the C, so it's 500 microfarads. Okay, and then this here is the voltage, okay, and we're getting the voltage here. So it's 40T is the voltage, but we have to square it, okay? So don't forget that square, so that has to be squared. Okay, 1/2 CV squared. Fairly straightforward. And then we calculate it out, and the energy is 0.4 T squared, okay? So it's pretty easy to square a function, so I like this method a lot. And then we can get a data point for at 2 seconds, right? That's the end of that time interval, and it's 1.6 joules. We see that, of course, it's a quadratic equation, so the graph is going up like that, and that's the value of, or the function, okay, in that piece for the energy. And it rises up to 1.6 joules at 2 seconds, okay? So that was fairly straightforward. What about doing it with the integral method? Okay, so we have the energy being equal to the integral of the power, so 0.8. And where is that coming from? 0.8 tau, actually. So 0.8 t, that's the power, okay? That's what we found as the power in that first piece, okay? So we're taking the integral of that, and we're taking the energy, the initial energy, which we know is 0, okay? So then we take the integral, we get a square, and then we see that we end up with 0.4 t squared, which is exactly the same as what we had when we did it with 1/2 CV squared. So that's great. The two methods are consistent with each other, and that's what we would expect, okay? Personally, I like the first way, the 1/2 CV squared, because taking integrals is, you can make more mistakes using that method. So let's do the next interval. So we're doing 2 to 3 seconds. Okay, so then we have 1/2 C V squared, so that 80, that's coming from here, okay? So that's the voltage in that middle interval between 2 and 3 seconds, okay? And then we have to square that, and we get Wt is equal to 1.6, okay? And that makes sense. It aligns with the previous piece that we set out. So that's right here, okay? So it joins the line, okay? At the same point, so that's perfect, okay? That's what we expect. Okay, so then, if we do the integral, so we have to use the power, and we know the power in that interval was 0, okay? So we get 0 for the integral, and we're taking the energy at 2 seconds, okay? And then, so the integral goes to 0, and the energy at 2 seconds was 1.6. We found that earlier. And then, so then the energy is equal to 1.6. That's the function during that interval. And it is the same as we found using 1/2 CV squared. So that's perfect. We know our math is correct. So then let's do the last interval. So we're doing this interval right here, 3 seconds to 5 seconds. So it's 1/2 C V squared. Okay, so that is V, and that's coming from that last piece for the voltage. Okay, and don't forget to square it. And we get this equation here, a little bit more cumbersome, but we can plot it. We get our data points. 3 seconds, it's the same as what we expect. That's where we're starting from the previous piece. And then at 5 it's going to go down to 0. Okay? So then we can just plot that line and then denote the function for that piece there. Okay? And then doing the integral, we'd have to take the integral of power, so that's here, and that comes from right here, okay? That comes from the power, okay, from that piece. We have to take the integral, and then we have to take the initial energy at 3 seconds, okay, at the start of this piecewise analysis. When we work out the integral, it's a little bit more complex integral than the previous one, or previous ones, but when we work it all out, we get the exact same equation for energy as we got using 1/2 CV squared. So in my books, this is the big winner, okay? This is much easier, but I wanted to show you the alternative method just so that you get a little bit more practice with the math, because sometimes you're going to be using integrals for these graphs, and I just wanted you to see a worked solution. Okay, so then let's interpret what's happening here. So in this first piece, the first interval, 0 to 2 seconds, the capacitor is charging, okay? So the power is going up, like what we said. So it's positive and it's increasing, so it means that the capacitor is charging, and we see the energy is increasing. Okay, so that means that the capacitor is getting more and more energy. Okay, and then on the other side, we see the capacitor discharging on the last interval from 3 to 5 seconds. Okay, so then we see, you know, the power is negative and it's going down to 0, so it's discharging and discharging. And we can see that the energy itself is going less and less down to 0. Okay, so the capacitor is discharging in this interval. Okay, and there's something interesting to note. Now remember, the energy in a capacitor is 1/2 CV squared. Okay, 1/2 CV squared. So that can never be negative. It can never be negative. Okay, so then we will never have like the capacitor line, you know, coming up and then going down negative and coming back up again. Okay, it can never go negative because that equation is never negative. So the energy is always positive or 0 in a capacitor. Its voltage can go negative, even though in this case, you know, we drew this voltage waveform as positive. If for example this negative current kept going and didn't go to 0 but just kept going, then this capacitor voltage would continue to the negative direction, and it would be charged in the other direction. Okay, so now in terms of how to handle these kind of equations, let's say you get it, this kind of question that you may get on an exam. What happened here? What did we do with this analysis? So first, we were given a current, okay? We were given this current waveform, and we were given a circuit, okay, that's associated with it. And then what we did is we used this equation here to calculate the voltage, okay? So this equation takes the current, right, and gives you a voltage, okay? So that's what we do. We use that equation, okay? So that's a very useful equation. So we went in that direction. We went from current to voltage, okay? Fair enough. But we can also, instead of giving you the current, we can give you the voltage across a capacitor and ask you to calculate the current, or to get or obtain the current waveform, and then calculate the power and energy from that. So if you happen to be given the voltage waveform, what you would do to obtain the current waveform from that is use the relation that we know, I is equal to C dV dt. Okay, so you got to work with the equations and relationships that you know. And then, so you would take the derivative of the voltage, right? So this is the derivative of the voltage, and you multiply it by the capacitance. So where do you get the voltage from? Well, you're going to have to get like the functional representation of the voltage, you know, in each of the pieces if it's given like this. So you take the derivative of that, okay, multiply it by the capacitance, and then you will obtain your nice current waveform. Okay, so these kinds of questions typically appear on the final exam. You can get one for a capacitor like what we've done now, or you can get one for an inductor, which we will do in a later lecture. Thank you.